Module 8, page 66. Statistical Reasoning in Everyday Life. The Need for Statistics. For psychologists using descriptive, correlational, experimental, and other research designs, statistics are the tools that allow them to measure variables and then interpret results. Yet, accurate statistical understanding benefits everyone. To be an educated person today is to be able to apply simple statistical principles to everyday reasoning. We don't need to memorize complicated formulas to think more clearly and critically about data. Off the top of the head estimates often misread reality and mislead the public. Someone throws out a big round number. Others echo it, and before long, the big round number becomes public misinformation. 2 examples. 10% of people are gay or lesbian. Or is it 3 to 4%, as suggested by various national surveys? Module 50. We ordinarily use 10% of our brain, or is it closer to 100%? Module 12. The point to remember: doubt big, round, undocumented numbers. If you read that there are 1 million missing children, 2 million homeless, or 3 million spouse abusers, you can be pretty sure that someone is guessing. If they want to emphasize the problem, they will be motivated to guess big. If they want to minimize the problem, they will guess small. Statistical illiteracy also feeds needless health scares. In the 1990s, the British press reported a study showing that women taking a particular contraceptive pill had a 100% increased risk of blood clots that could produce strokes. This caused thousands of women to stop taking the pill, leading to a wave of unwanted pregnancies and an estimated 13,000 additional abortions, which are also associated with increased blood clot risk. And what did this study actually find? A 100% increased risk, indeed, but only from 1 in 7,000 to 2 in 7,000. Such false alarms underscore the need to teach statistical reasoning and to present statistical information more transparently. Descriptive statistics. Once researchers have gathered the data, they may use descriptive statistics to measure and describe characteristics of the group under study, similar to the way teachers use descriptive statistics to assess how their students have performed. One way to do this is to convert the data into a simple bar graph called a histogram, as in figure 8.1, which displays a distribution of different brands of trucks still on the road after a decade. When reading statistical graphs such as this one, take care. It's easy to design a graph to make a difference look big or small. The secret lies in how you label the vertical scale, the y-axis. The point to remember: think smart. When viewing graphs, read the scale labels and note. Page 67. Measures of central tendency. The next step is to summarize the data using some measure of central tendency, a single score that represents a whole set of scores. The simplest measure is the mode, the most frequently occurring score or scores. The most familiar is the mean, or arithmetic average, the total sum of all the scores divided by the number of scores. The midpoint, the 50th percentile, is the median. On a divided highway, the median is the middle. So too with data, if you arrange all the scores in order from the highest to the lowest, half will be above the median and half will be below it. In a symmetrical bell-shaped distribution of scores, the mode, mean, and median scores may be similar. Measures of central tendency neatly summarize data, but consider what happens to the mean when a distribution is lopsided, when it's skewed by a few way out scores. With income data, for example, the mode, median, and mean often tell very different stories. This happens because the mean is biased by a few extreme incomes. When Microsoft co-founder Bill Gates sits down in an intimate cafe, its average mean customer instantly becomes a billionaire. But the median customer's wealth remains unchanged. Understanding this, you can see why, according to the 2010 U.S. Census, nearly 65% of U.S. households have below average income. The bottom half of earners receive much less than half the national income cake. So, most Americans make less than average, the mean. Mean and median tell different true stories. The point to remember: always note which measure of central tendency is reported. If it is a mean, consider whether a few atypical scores could be distorting it. Page 68. Measures of variation. Knowing the value of an appropriate measure of central tendency can tell us a great deal, but the single number omits other information. It helps to know something about the amount of variation in the data, how similar or diverse the scores are. Averages derived from scores with low variability are more reliable than averages based on scores with high variability. Consider a basketball player who scored between 13 and 17 points in each of the season's first 10 games. Knowing this, we would be more confident that she would score near 15 points in her next game than if her scores had varied from 5 to 25 points. The range of scores, the gap between the highest and the lowest, provides only a crude estimate of variation. A couple of extreme scores in an otherwise similar group, such as the $950,000 and $1,420,000 incomes in Figure 8.2, will create a deceptively large range. The more useful standard for measuring how much scores deviate from one another is the standard deviation. It better gauges whether scores are packed together or dispersed because it uses information from each score. The computation assembles information about how much individual scores differ from the mean, which can be very telling. Another example, if your high school serves a community where most families have similar incomes, family income data will have a relatively small standard deviation compared with a community with more diverse incomes. You can grasp the meaning of the standard deviation if you consider how scores naturally tend to be distributed in nature. Some data have no clear pattern, whereas other data may take the form of a bimodal distribution, which means that it has two peaks or humps, modes. We can imagine a simple behavioral example, a town's intersections, traffic volume across 24 hours, with peaks at the morning and evening rush hour. However, large numbers of data, heights, weights, intelligence scores, grades, though not incomes, often form a symmetrical bell-shaped distribution called a normal distribution. Most cases fall near the mean, and fewer cases fall near either extreme. This bell-shaped distribution is so typical that we call the firm it forms the normal curve. As Figure 8.3 shows, a useful property of the normal curve is that roughly 68% of the cases fall within one standard deviation on either side of the mean. About 95% of cases fall within two standard deviations. Thus, as Model 38 notes, about 68% of any group of people taking an intelligence test will score within positive or negative 15 points of 100. About 95% will score within positive or negative 30 points. Page 70, Inferential Statistics. Data are noisy. The average score in one group, children who are breastfed as babies conceivably differ from the average score in another group, children who are bottle-fed, not because of any real difference, but merely because of chance fluctuations in the people sampled. How confidently, then, can we infer that an observed difference is not just a fluke, a chance result from the research sample? For guidance, we can use inferential statistics to determine how reliable and statistically significant the differences are. This way, we will know if the results can be generalized to a larger population. When is an observed difference reliable? In deciding when it is safe to generalize from a sample, we should keep three principles in mind. Number 1, representative samples are better than biased samples. As noted in Module 5, the best basis for generalizing is not from the exceptional and memorable cases one finds at the extremes, but from a representative sample of cases. Research never randomly samples the whole human population. Thus, it pays to keep in mind what population a study has sampled. Number 2, less variable observations are more reliable than those that are more variable. As we noted earlier in the example of the basketball player whose game-to-game points were consistent, an average is more reliable when it comes from scores with low variability. Number 3, more cases are better than fewer. An eager high school senior visits 2 university campuses each for a day. At the first, the student randomly attends 2 classes and discovers both instructors to be witty and engaging. At the next campus, the 2 sampled instructors seem dull and uninspiring. Returning home, the student, discounting the small sample size of only 2 teachers at each institution, tells friend about the great teachers at the first school and the bores at the second. Again, we know it, but we ignore it. Averages based on many cases are more reliable, less variable than averages based on only a few cases. After noticing that small schools were overrepresented Among the most successful schools, several foundations invested in splitting larger schools into smaller ones without realizing that small schools were also overrepresented among the least successful because schools with fewer students have more variable outcomes. Again, more cases make a more reliable average. The point to remember: smart thinkers are not overly impressed by a few anecdotes. Generalizations based on a few unrepresentative cases are reliable. When is an observed difference significant? Let's say you compared men's and women's scores on a laboratory test of aggression and found a gender difference, but individuals differ. How likely is that the difference you observed was just a fluke? Statistical testing can estimate the probability of the result occurring by chance. Here's the underlying logic. When averages from two samples are reliable measures of their respective populations, as when each is based on many observations that have small variability, then their difference is probably reliable as well. Example: the less the variability in women's and men's aggression scores, the more confidence we would have that any observed gender difference is reliable. And when the difference between the sample average is large, we have even more confidence that the difference between them reflects a real difference in their populations. In short, when sample averages are reliable and when the difference between them is relatively large, we say the difference has statistical significance. This means that the observed difference is probably not due to chance variation between the samples. In judging statistical significance, psychologists are conservative. They're like juries who must presume innocence until guilt is proven. For most psychologists, proof beyond reasonable doubt means not making much of a finding unless the odds of it occurring by chance, if no real effect exists, are less than 5%. When reading about research, you should remember that, given large enough or homogeneous enough samples, a difference between them may be statistically significant, yet have little practical significance. In one study of nearly 700,000 Facebook users, researchers exposed people to status updates with more or less positive words. Given the supersized sample's statistical power, the tweaking produced a statistically significant but trivial effect. For example, those who received fewer posts with positive words responded with 0.1% fewer positive words themselves, a statistically significant effect, though one too tiny to be meaningful in the real world. Comparisons of intelligence scores among hundreds of thousands of firstborn and laterborn individuals indicate a highly significant tendency for firstborn individuals to have higher average scores than their laterborn siblings. But because the scores differ only slightly, this significant difference has little practical importance. The point to remember: statistical significance indicates the likelihood that a result could have happened by a chance, but this does not say anything about the importance of that result.